All right, welcome everyone, those here and those at home. It's a pleasure to welcome you to this third edition of Solstice of Foundations. So it's a summer school on quantum foundations. And I'm very happy everyone found the room and the coffee breaks and everything. So please hold on to your mug. We'll talk about this later. So how the school is structured is that in the first few days you get a bit of basics of quantum foundations. So we start today with John Selby from Gdansk, who will tell us about a framework within which we can see quantum theory as a special case, right? And we can look for ways of why quantum theory is the way it is, from like information theoretical axioms instead of just giving. And in the afternoon, Paul Skrzypczyk from Bristol will talk about non-locality and several aspects of non-locality in quantum theory. And then we start talking, this is like the mini basics, and then we start talking a little bit deeper. So Matt Liefer will join us online from Chapman University, and he'll talk about trying to look at kind of hidden variable theories for quantum mechanics, or what he'll call more generally epistemic theories, and the issues with that, and the kind of things there. And then following on that, David Schmid, also from Gdansk, will talk about non-contextuality, and we'll go quite deep into this. And then, because sometimes it might seem that all the strangeness of quantum mechanics is because it's quantum mechanics, we'll have Gemma de las Cuevas come from Innsbruck and tell us about, there's actually many theories that have problems and paradoxes and this incompleteness issues. And so she'll talk about universality and incompletude. So it's like versions of Gödel theorem that you can find not only in physical theories, but in any kind of logical framework. Good. And then after this, we'll have Vicky, right, from ICFU Barcelona, who will tell us about now, maybe many of you have some quantum information background, but not so much foundations, but maybe you've learned some techniques there, like STP semi-definite programming or so on. Or maybe you're interested in seeing like, how do things that we learn in foundations relate to the more traditional practical quantum information theory. So Vicky will talk about this. She'll see about how to apply techniques from information theory into foundations and vice versa. And then, again, talking about relation to other topics, we will have Konstantinos from Cambridge Quantum and Quantinuum. We'll talk about something that started as a foundations approach to quantum mechanics, which is like at some point exploded in a different direction, and now they're using this to talk about linguistics and natural language processing, which is a very technology in general and machine learning. And so we'll talk about this, and this is also a way of saying like, oh, we do foundations, but it can also be useful. And finally, tomorrow we have an interactive session with Damien Nguyen from Huawei. So he'll talk about Project Q, which is an open source quantum computing software. And then Nuria will talk about like how one can use this to design quantum thought experiments. And then he'll have a go at trying to program your own interpretation of quantum theory, for example. Okay. I think that's all of the lectures. Yes. So, no, it's not. We'll have Esteban Castro from ETH Zurich, who will talk about quantum reference frames, which is also, again, a topic that's a bit different from everything else we'll talk here, but again, very useful even outside foundations. So how to decide what directions are, how to decide what time is. This is all in terms of physical systems that we measure, like a clock or a compass or so. And he'll talk about what happens when these systems are quantum systems and how broad we can go here. Okay. And so before we start, I should let you know that this was sponsored by the Quantum Center of ETH Zurich and Quantinuum and Huawei. So there will be short presentations by people from these three institutions. And also at the dinner, there will be a little career fair, so people will have some stalls there, and you can go and talk to them about careers in these places. I think in particular Quantinuum are very keen on internships and all sorts of things like this. Yes. And so if I cannot answer it in a moment, I'll interrupt the lecture and I'll ask them. Yes. And John also said that he wants you to ask questions during the lecture. Very good. So without further ado, I'll leave with John Selby from Gdansk.
There we go. OK, that's working. Excellent. Oops. So, hello, everyone. And let me start by thanking the organizers for inviting me to speak. It's quite an honor to be doing the opening session, so hopefully I don't disappoint. I think it's quite useful, though, that I'm doing the first of these sessions, because the things that I'm going to talk about, I think, can really form a foundation for other bits of foundations as well. So the things that I'm going to talk about, hopefully you'll see recurring a bit over the week. And so this will give a good starting point for the summer school. So in my talk, I'm going to focus on sort of theories other than quantum theory. So sort of hypothetical ways the world could be if it were not quantum. And I think a valid question to ask is, like, why should any of you care about this? Like, isn't quantum theory good enough? I mean, we've seen quantum theory has been phenomenally successful at predicting basically every experimental test that we've thrown at it. So why shouldn't we just go and study quantum theory? Why should you bother listening to me talking about these sort of hypothetical other theories? So there's various reasons why I think this is worth doing. The first is that quantum theory might not actually be fundamental. We know it's been successful so far, but we also thought that classical theory was great for a long time, and then suddenly we discovered phenomena like the photoelectric effect, and we had to totally rethink our view of the physical world. So maybe the same will happen one day with quantum theory, and we'll need to look at alternative theories. And so if we've made a start and have frameworks for talking about these things, then we will hopefully be ready for such an eventuality. But it's not just for sort of this hypothetical future where we discover something wrong with quantum theory that this is useful, but also it helps to contextualize quantum theory itself. And I wanted to give an example of, to get you in the right mindset for this, which is, consider you ask a biologist, OK, explain to me why a tiger has stripes. Then they're probably not going to just sort of look at the tiger on its own and start cutting it up and trying to understand why it's got stripes. I mean, they might at the end of the day say, oh, it's DNA, that's the answer. But this isn't a very satisfying answer. Instead, they would probably say, well, let's look at the tiger in its environment, where it's trying to hide from prey and sneak up on them and so on. And so the real explanation is that, well, it helps it to blend in with its environment, and so it can eat food and live and do well, and so on. So we understand the object by putting it into sort of the context in which it exists. Theory and saying, why is quantum theory like this? Oh, well, it's because Hilbert spaces. Like, this isn't a satisfying explanation. Instead, we put it in the context of a framework of other, because we've got these intuitive ideas about how the world works. It should work. So looking at other theories helps us to understand quantum theory better at the end of the day. Another reason to study these alternative theories is that sometimes they do actually represent genuine physics. So maybe we look at some like experimental capabilities on a quantum computer, say. So these alternative theories may actually be useful in certain practical situations too. But I think the main reason why I study these things is basically just because it's fun. It's entertaining to me, at least, just to sort of contemplate the different ways that the world could have been and to see what weird properties these other theories have. Essentially, to my mind, it's like science fiction, but mathematics. ways that people have used to study sort of alternative physics. Like, this is not a new topic. It's existed basically since quantum theory itself was discovered. So this isn't new, and there's been many different approaches over the years. But I wanted to just give like a big picture of broadly how these different approaches fit together. So, okay, the first sort of way of studying alternative theories is basically just by looking at sort of modifications of existing theories that we know. So we take quantum theory and we tweak it in a small way, or classical theory and we tweak it in some small way, and we see what happens. So examples of this kind of thing are things like the nonlinear things like collapse models. And I'm not really going to get into this stuff very much, but just to say that there is this approach that you can take. Another approach that you can take is to focus on a particular phenomena that might exist in quantum theory, such as non-locality that Paul is going to talk about, or contextuality that David's going to talk about. And then you can just focus on this particular phenomena and say, what is sort of the scope of logical possibilities for this particular phenomena? And then there's the sort of third approach, which is my favorite approach, which is to sort of build a mathematical framework for describing these possible theories of physics. And to build this framework on sort of mathematical principles that are well motivated by some physical principles that we care about. And so there's a huge number of these frameworks, and I'm going to talk about a couple of them in these lectures. Thanks. So the main framework that I'm going to talk about is called in particular, generalized probabilistic theories or operational probabilistic theories, which are extremely closely related concept. And in tomorrow's lecture, so today's lecture is going to be focused on process theory, kind of look at GPTs and OPTs, but we're kind of going to view them through the lens of process theories. So it's like a special case almost. And I think arguably, I would say that it's the best way to study also particular phenomena and works. So for example, if you want to study non-locality, it's nice to be able to know that there's a particular physical theory that can be expressed as a GPT that can underpin the scope of possibilities for this phenomena that you're studying. Similarly, if you want to study modifications of quantum theory, I think it's important to know that these are like mathematically consistent modifications, and that, and again, sort of the best way to do that is to take these modifications and recast them in one of these frameworks and see, okay, does this modification I've designed actually make sense? Is it consistent? But this is sort of a personal preference thing. Lots of people do things in different ways, and for me, I like this sort of principled framework-based approach. I said I'm going to talk about process theories today, so let me try and get started on this. I could ramble on for ages, but time is limited. So process theories, on the one hand, can be understood on a very mathematical level, based on the mathematics of symmetric monoidal categories. And this is a really useful perspective, but it's not the perspective I want to take today. And essentially, I don't want to take this perspective today because I would probably have to spend the entire first lecture just putting the basic definitions of what a symmetric nodal category is. And this is not very interesting, to be honest. At least not to me. To mathematicians, sure, but for me, it's not so interesting. The perspective I like to take on process theories is really that it's just a mathematical formalization of the kinds of diagrams and sketches that you guys have probably drawn in physics courses for help guide what we're doing in a calculation just to keep track of what's going on. So in a Bell experiment, for example, we might draw something like, you have Alice and Bob, and they have some shared state, and the shared state is passed Alice and Bob, and then they do some manipulations of it. And we might draw that as a little sketch, but then go and write down a linear algebraic expression to formally describe it. What process theories let you do is say, OK, I've got this little sketch. I'm just down the linear algebraic expression. I'm going to work entirely with the diagrammatic formalism itself. So that's how I view these things, really. And I'm going to try and introduce things in that light. I've made some lecture notes, and I'll add to those as the week goes on. And I'll put references to these alternative perspectives into those if you want to see the more sort of mathematical perspective on things. OK, so a process theory, sort of the key component in a process theory, as the name might suggest, is a thing called a process. And we diagrammatically draw these by labeled boxes. So this is a process P. And a process will have some input systems, which are drawn by these wires. And these have some names. So this is like a process P with inputs. Maybe it's got B also as an output, but some other systems as well, so some C and some A. I want to quickly switch to slides for... how do I do that? Undo that. Yeah, nice. OK. So the kinds of things that you might have in a process theory might be something like this, some sort of physical example. I think this is spontaneous parametric down conversion or something. Anyway, it's something that a photon comes in, and it splits into two photons that go out again. And then you might also have something, a process which is like a photon detector, which has a photon that comes in, and then some outcome, like a click or not to click, as sort of the output. Food and gives you as an output noise and poo. Or algorithm that sorts lists in some sense. So it's got a list coming in, and then you get a list coming out, but the output list now is sorted in some sense. So these are all examples of the kind of processes that you might encounter in a process theory. So it's a very broad framework and describes biology, chemistry, physics, mathematics, computer science, and so on. Like, it's very widely applicable. And the key thing you can do with processes once you have them is you can start wiring them together to form things we call diagrams. Well, we've got this photon splitter thingy. Then we want to put a detector on one wing of this and see if the detector clicks or not. So this would be described by this kind of diagram. It's sort of the intuitive thing that you would have drawn in your notebook if you were trying to describe this kind of experiment to someone. But the important thing about drawing diagrams is that you want the types to match. So there was a pointer thingy. There it is. So here it's important that sort of the output of this process was a photon, and the photon can go into the detector. So this makes sense as a diagram. Whereas if we have a diagram such as this one, then it doesn't really make sense. Like, we might want to try and wire the poo outcome of the baby into some sorting algorithm, and this just doesn't make sense. So we don't allow diagrams where the sort of the system types, as we call them, don't match up properly. This would just be not a valid diagram. The other kinds of diagrams that we don't allow are ones where we end up having cycles. So we don't want to allow, I don't know, this photon that comes out. I should say this isn't sort of a universal constraint. There might be times where you would want to have this in a process theory. But for the kinds of process theories that we're going to talk about, this is really a bad idea. Essentially, it allows you to have things like the grandfather paradox, where you have an outcome system, maybe that's you, going back and looping around and deciding whether to kill your own grandfather or not. We want to avoid having to talk about this kind of paradox, so we just sort of forbid from the start diagrams that end up with cycles, where the types all line up and make sense. So this is just some sort of abstract diagram. I couldn't be bothered to try and think of a nice physical example here. But you get a bunch of equalities for diagrams. And the rough idea is that only how the processes are wired together matters. It doesn't matter exactly where they are on the page. This is sort of irrelevant information. So you can see that these two diagrams have the same connectivity on both sides. You have an input into G. The right-hand one goes off to the E. Left one goes off to H. And then the two systems of H go off to the left. And then you have this system F going over to here. And you can see that that's exactly the same description on the right-hand side as well. We've just sort of shuffled around the processes, but left how everything is connected together the same. One important thing to note is that it's not just how sort of the processes are connected together that matters, but also really how the systems connect to sort of this imaginary boundary that we could draw here. So it matters that we have A and then B. If I put sort of a swap and put B and then A instead, then that would be a different diagram. So these two are not the same diagram because we've swapped over the order of the outputs. So the way to intuitively think about this is we've got sort of a box defining the boundary, and the processes are wired to the boundary as well as to each other. And as long as we keep that wiring to the boundary and the wiring to each other the same, we're free to shuffle around the processes on the page. OK, I think I now need to switch back, so let's turn that off. OK, so we've seen sort of processes, we've seen diagrams, we've seen sort of when two diagrams are the same diagram. Typically, though, we don't just get sort of equalities that say that two diagrams are the same in the way I was just describing. We also get some extra equalities. So we sort of have the basic equalities that I just was discussing, and then we get some extra ones. And these form part of the definition of a process theory. But to try and give an idea of what we're talking about, you could imagine that we had this process sort, which had a list as an input and a list as an output. Well, we all know that sort of if we apply this algorithm twice, we're going to get the same thing, right? It does the same thing. It just sorts the list. So then we should have equalities. I can move that up rather than kneeling down. Like this. If I sort twice, it's the same as sorting once. So figuring out what all of these equalities are that you have between out the definition of a process theory. So that said, let me actually define what a process theory is. So I've talked about sort of processes, all the different kinds of processes you could conceive of. what a process theory is, it sort of picks out a particular world of processes that we're interested in. So we pick out some collection of processes that we want to use to describe the phenomena of interest. So maybe we pick out quantum processes or classical processes or biological processes or chemical processes, and we define a process theory for that particular thing that we're interested in. So a process theory is a collection. We're going to denote a process theory by calligraphic P for this course. So it's a collection of processes. But it's not just sort of an arbitrary collection of processes. Very importantly, it's a collection of processes which is closed under forming diagrams. So if we have some subset of the processes in this collection, and I can wire those together to form a valid diagram, then that diagram itself has to be a valid process in this process theory. The writing bigger. OK. I will try. Is that definition, can people see that, or should I rewrite that bigger? OK. It's also in the lecture notes, which I put on the Discord, so feel free to look at that. My handwriting is quite bad, so feel free to shout if things aren't clear. OK, so that's the basic definition of a process theory, and hopefully things will become a bit clearer as I give some examples of these things. But there's a bunch of sort of special processes that often appear in process theories, and it's important to sort of have some basic jargon that we can use to talk about these. So the first kind of special process that we have are ones that don't have any input. And we tend to draw those as triangles like this. Really, the precise shape I draw a box is kind of irrelevant. It's just sometimes useful to help distinguish different kinds of things. So often the ones without an input will draw as a triangle just to make it sort of more obvious there's no input. And these are known as states or maybe preparation procedures. They're something where there is no input to them, and then we end up with some system, some physical system that's prepared according to this process S. So those are states. Similarly, we often have processes that don't have an output, and we'll talk about these quite a lot more later. So this is something that takes an A in, and then nothing comes out of it. And these are generically called effects. And then if I take a state and I plug it into an effect, well, then that gives me something that doesn't have any inputs or outputs. And these are known, I didn't want to use S for that. Let's just call that R. So these things are known as scalars. What else do we have? We also often identify sort of bits of wiring as processes as well. So for example, if I have just a bit of wire on its own, then I can imagine that there's something going on here. Well, nothing going on here, but I want to view this as a process, and this is the identity process. It leaves everything else invariant if I compose it with it, because it's just a bit of wire. More interestingly, though, is that I think we've seen in some of the diagrams, we can have things that look like this. Actually, so we've seen bits of wiring in our diagrams that look like this kind of thing. So this takes AB to BA. And we can sort of pretend that this thing is also a process, and this is known as a swap. These are the kind of special processes that we'll often talk about, so it's useful to know about these. We also have special kinds of composition. Which are just examples of forming diagrams. So in particular, it's useful to talk about sequential composition, which is just plugging two processes together in sequence. I know that this kind of composition is only defined if the output of F is the same as the input of G. And we denote this, we kind of have a symbolic notation for this, which is sort of G, and then a little circle, F. We also have parallel composition. Which is just sort of when we don't wire two processes together again, we just sit them next to each other on the page. And we denote this by the sort of O times tensor product symbol. This very often has absolutely nothing to do with the tensor product that you might be used to in quantum theory. Sometimes it is, but other times it can just be some other mathematical thing next to each other.
Is there a reason why there's one wire on the left and two on the right?
Because I made a mistake. Thank you. I guess it's important to say that sometimes we do formalize that mistake, and we can write things like, we can also imagine that we've got some sort of composition for the systems as well, and then we get this kind of equality. I'm going to because it ends up leading to confusions. So it's better just to leave sort of, when you have composite wires, to just draw them as composite wires. Until you get to complicated things, and then you need a shorthand note. That should be enough. And there's a final special process that I was meaning to talk about that I forgot about. And pretend that these are processes like the identity and the swap. We can also draw a dashed box around absolutely nothing at all. And this is a scalar in the sense that you can think of it as a process happening at all, in fact. And this is kind of acts as the number one for your process theory, in that if I compose this with any other process at all, then I just get the process back. So this is like the number one in that sense. And this sort of, these special processes that I've introduced are useful because they make connection to the categorical presentation of things that I briefly mentioned at the start. Essentially, you can show that any diagram that you care to draw at all, provided that it has these type matching constraints and is acyclic, as we're demanding, can be built up out of sequential composition, parallel composition, identities, swaps, and the basic processes in the process theory. So this is, in some sense, like a universal set of composition rules. If you formulate things in that categorical language, though, then you have to put in a huge number of sort of rules that say for how these different notions of composition interact with themselves and each other. Whereas in the diagrammatic language, all of these things fall out for free, basically. So, for example, you can show very simply that this sort of tensor product, or so if I have something like F composed with G composed with H, Then symbolically, I would have to specify the order that this is happening in. So I have to say, well, first I'm going to compose G and H, and then F. Diagrammatically, though, this is just sitting the three things side by side. So there's no sort of ordering. There's nothing that says I first compose G and H and then combine this composite with F. It's just immediate that the three are treated on an equal level. F composed with G, composed with H. So that these kind of axioms that you might expect to have to introduce for binary operators like associativity, unitality, and so on, they all just come out for free from the diagrammatic formulation. So this is why I like the diagrams, basically. It saves you a lot of work. You just write out the diagrams, you look if they're the same, and if they're the same, then you're done. You don't need to sort of go down to some axioms. Okay, so this is the very basics of a process theory. I wanted now to give a slightly non-trivial example. And because it's slightly non-trivial, I didn't want to draw it on the board. So here it is. We have the process theory of how to brew beer. So as a process, we have brewing, which has yeast, hops, malts, and water as an input. And then we get bottles of beer as an output. And this isn't a very useful description of how all of this works. Instead, you want to sort of say that this is equal to some more complicated diagram in your process theory that actually tells you how it all works. I would like to spend the next 20 minutes talking about this, but I probably shouldn't, because we should talk about quantum physics. But hopefully this gives you the idea of how these things can be used, that we can sort of take some complicated process and break it down into simpler steps that we can understand. And then we get other sort of things we can then take. Once we've brewed the beer, we can compose it with other processes, such as this one. And the bottle of beer disappears, and you get the person left at the end. And these satisfy nice equations, such as this one. If you have a sober person and a bottle of highly alcoholic Belgian beer, and the person drinks the beer, then you end up with a drunk person.
On Discord, and this is a good example. So if they're on top, it's about the definition of equivalent or not. So if you then kind of twist the two, yeah, it's not the same diagram anymore, right?
Correct, yes.
And if you bring even if you bring the labels along, right?
Yeah, so they're very closely related diagrams because we've got the swap, so I can always swap them around, right. But they won't necessarily be the same, literally the same process. So to give an example of that, you could imagine that you have a sober person and a drunk person sitting next to each other. If I swap them around, it's not the same, right? It's different. The order of the people has swapped, and now it's a drunk person and a sober person.
Right. So in terms of how you compose it then with other things, the order where they are like on the page matters.
Matters, yes.
Okay.
Yeah.
Yeah.
But I mean, for example, in this diagram, I can pull the sober person over to here, the bottle of Belgian beer over to here, and that is equal. And that's equal because the connectivity is the same. So it's only when you sort of have dangle with the ordering of the inputs and the outputs.
So we don't need to be careful with the ordering of the inputs and outputs for one of the processes, right? So it doesn't matter if I leave the person and a bottle of beer, like on the person on the left, bottle of beer on the right, but I take the right wire to the left input and the left wire to the right input, it doesn't matter, right?
But they would be, you can do all of the same things with them, basically, because you can sort of freely swap things. So it's not strictly equal, but they're, from a sort of the perspective of a sort of resource, they're kind of equivalent resources. So you can do all of the same things with them, but on a formal mathematical level, you've got to be careful of what the ordering is, else you can make mistakes. Swap the two parties over. So it's important to keep track of the order, but you can also sort of always swap the order because we've got these swap processes around.
Is it a correct assessment to say that a process is essentially where an interaction happens?
Yeah, I think in physical examples that we'll get to, typically these processes are some sort of interaction. There's other kinds of process theories where you maybe think of things differently, but for the purposes of this lecture, yeah, these are kind of interactions between different physical systems.
Maybe the reason for why we cannot change probability and person, the whole process, is because the process drinking is, as you showed on the slide before, it's more like there's more behind it. And for example, drinking might be, I don't know, the person drinks, this is actually, I don't know, the liquid gets into the digestion system and then so on and so on. But this is why we cannot really exchange, because there might be other processes involved. The person has not the attributes of a person and therefore cannot go through the same process.
Yeah.
This is the reason why.
Yeah, I think that's a good way to think about it. That sort of another way to put it is that if I just look at the process drink on its own, you can't really see that there's a difference if I swap the two inputs over. But if I start either breaking drink apart into more complicated diagrams or composing drink with other stuff, then you'll see that it sort of matters whether I've done this swap or not. So yeah, on its own, it's kind of irrelevant, but when you start comparing it to other things, then it matters more.
Do you already assume linearity?
No, so I've not mentioned any linear structure at this point. We'll get there shortly.
Because you made a statement that you cannot consider after the SPDC the photon coming back to,
Yeah.
photon going into the SPDC. So that sort of a grandfather paradox is already ruled out.
Yeah.
But those are the nonlinear structures which give rise to grandfather paradox. So when you say that you don't consider them, you already assume linearity for them.
So I would say at this point there's no notion of ruling out these sort of time loops means that when we do get to an example with linear structure, then things are going to end up being nice and consistent. Whereas if at this point I'd allowed loops, then when I try and put in linear structure later, we'd have issues.
Could you show diagram 6?
Yes. Here we go.
I was just wondering that water.
Very good.
That's an effect.
Yeah, so casually drew this little symbol here and didn't talk. So how this chiller works is that it's a big coil of copper wire, and you feed water in at one end, and water comes out at the other end, and that water you just pour down the sink. It's very environmentally wasteful. But yeah, this symbol then represents sort of pouring the water down the sink. And this symbol is used in many different process theories, and it can represent pouring water down the sink, or it can represent throwing some system in the bin, or maybe in other contexts will represent just ignoring some system that we don't really care about anymore. So there's lots of different meanings. There's a bunch of consistency conditions that it has to satisfy. So I'd like to talk about those consistency conditions now. Okay, that's as low as that goes. So So as I was saying, we have this process called discarding. So now I'm going to focus on a particular kind of process theory that has these discarding processes, discarding effects around. So this is an effect because it's got an input but no output. And these are quite ubiquitous in physical theories. Got these discarding processes around. And these satisfy some nice equations. So if I throw away system A, one after the other, say, then at the end of the day, this is the same as discarding them both. So this is sort of an obvious kind of equation that you would want to demand of these things. And then we say that some other process is a discard preserving process if it satisfies this equation. So the process F maybe goes from A to B. This is the same as just directly throwing away system A. It doesn't really matter that I've manipulated A in some sense, because at the end of the day, it's in the bin. It's the same process. You might try and come up with counterexamples to this and think of physical processes that fail to be discard preserving. And typically, in these cases, what's happened is that you've not paid attention to some output. So if I have some extra output, C, then this equality certainly should not hold. So it's really only if I throw away all of the outputs that we very commonly will expect this equation. And I think this is a good thing to know about process theories, really, is that things really make sense and hang together nicely when you make sure that the processes that you draw have all of the relevant inputs and outputs drawn. If I start forgetting about some of them or trying to treat some of them implicitly, then you can often run into confusion. So if in doubt, draw all of the systems that you think matter. Later on, you might be able to pare it down and ignore some of them, but it's better to draw too many systems than too few. And very commonly we'll be in a process theory where all processes are discard preserving. And this is what is known as a causal process theory. Wrong one. This is known as a causal process theory. And as I said, this is a process theory, PT, where all processes are discard preserving. How am I doing for time, by the way? What? Oh, wow, OK. So in which case, I might skip the next thing I was going to say. In detail, at least, it's in the lecture notes. But the basic idea is that the reason why this is called a causal process theory is because if in a theory you have all processes discard preserving, then this ensures sort of compatibility with causality, in that you can only send influences if you've got some system propagating from one party to another. You can't just sort of get non-local things happening. You've always got to mediate influence with some physical system. And so this class of process theories satisfies that condition. OK, so the next thing that I will talk about is sort of a key example, which we're going to refer to a lot. And this is called stuck. stock for stochastic. And this is going to be our sort of representation of classical physics, basically. And I'm going to start here rather than starting with quantum physics, basically because it's much easier to describe. And it'll be useful when we start talking about generalized probabilistic theories in the next lecture. Have systems X and Y, for example, which are just finite sets. And the processes, I'll label by S, are stochastic maps between these finite sets. So to give a very simple example of what this kind of thing is, we can imagine that X is some sort of binary set with elements x1 and x2, and maybe Y is, well, I'll also do it as a binary set just to keep things simple. And then a stochastic map tells you what set. So we can think of this as like a time-ordered process. If at time t1 we have x1, then with some probability p, it's going to go to y1, and then with some probability q, it's going to go to y2. And similarly, x2, maybe x2 definitely goes to y1, for example. So formally, we can write, well, I guess it's worth saying that there's consistency conditions. For example, we know that x1 has to go somewhere. It's got to either go to y1 or y2. So we have consistency conditions such as p plus q. And similarly, because x1 can only go to one place, then we have that r equals 1. To more formally define these things, we can say that S is a function going from the Cartesian product of x and y. So that's all pairs, little x and little y. And for each pair, we get some value between 0 and 1. For example, we'll denote the S of y given x. So this is like a conditional probability distribution, basically. It tells me for each possible value of x, what the probabilities of y are. Sum over all of the values of y in the output set. Of x. For the sake of time, I won't go into the full generalization of this, but just to say that if I now have multiple inputs and outputs, I can define something very analogous to this. Essentially, I just have the Cartesian product of the input sets and the Cartesian product of the output sets, and then everything stays the same. But this is really the intuitive picture I want you to have in mind. So to give a couple of examples, well, okay, and then the other important thing to say is about composition of these things. And we're going to look at this form of composition. And the reason for looking at this form of composition is that you can of this. So sequential composition I can get basically by taking these outside systems to be non-existent, or sometimes we'll say that we take these to be the trivial system. It's kind of equivalent. And then you can see if all of these systems aren't there, then I just get sequential composition of S1 and S2. Similarly, if I ignore this middle system, make this not have a system or make it the trivial system, then really that's the same as the parallel composition of S1 and S2. Because if this middle system isn't there, then I can sort of take them and slide them to be next to each other. So if I define what composition looks like for this thing, then I also cover all of those special cases as well. So W and R. Then, okay, S1 is given by some conditional distribution, little r, little v given yz, and S2 is given by some conditional distribution u, w given x, r. And then this whole thing now has 3 inputs and 3 outputs. So this, we want to go to some S, which is going to have uwv given x, y, z. And the way we do that is just by summing over these values of r. So if I sum over the values of r, then I get the conditional distribution with these 3 inputs and these 3 outputs. OK. This is x, y, z, u, w, v. Should I rewrite this, or is it just about OK? OK. S2 of u, w given x, r, S1 of r, v given y, z. This equals S u, w, v given x, y, z. There we go. So this is how our stochastic processes compose with one another. To try and give a bit of more intuition for this kind of stuff, let's look at some special cases. So no input. And this, then, by our definitions, is a map from x to 0 to the unit interval that takes value x to So this is just a probability distribution, right? We get a bunch of values in the unit interval. An input and with an output are just probability distributions. If I then take this probability distribution and I feed it into some stochastic map, then, and I use this rule for this special case, then I get some distribution over y. So this is some q over y, where q of y equals the sum over x's in x of s of y given x, p of x. So this is just the standard sort of belief propagation formula. You have some probability distribution over x, you have some stochastic map or some conditional distribution, and that propagates our distribution over x to a distribution over y. We also have a discarding map. And in fact, there's only one effect in this process theory for each system, and it is this discarding map. And this is, so this takes y to the unit interval, and in particular, it takes element y to 1. And I think this thing looks a bit funny, and basically it makes a lot more sense when you start to use it in practice. So let's look at the following diagram. So suppose we have some probability distribution P. Now it's a bipartite distribution over x and y. And now let's look at throwing away y. Well, we can use the rules that I've set up. And this thing now maps, how to say it? Well, yeah, so this gives us some q of x, where q of little x is the sum over y in y of p xy. So we can now see what this discarding map is doing. It's basically telling us how to compute marginal distributions. We have some bipartite distribution p, given by p of x and y, and then we sum over the different values of y, and we get q of x, which is, as we all know, the marginal distribution over x. So this thing, in this context, in this process theory, is marginalization. I think it might. Yeah, I think this is a good place to stop. So I will continue this in the next lecture.
Right, so we start at 1/4 so we have 6 minutes bathroom break.
It is now. Am I starting off again?
Yes, and you can start by answering this question on Discord.
Yeah, okay, so there was a question on Discord which was basically about the relationship between sort of some process and what happens when we swap over the inputs and the outputs. So maybe let me try and just go into a little bit more detail on this, and hopefully this will answer the question. So to give some idea, like imagine we've got some state S. Well, we can talk about the stochastic processes, in fact, to give a concrete example. So imagine this is a probability distribution over x and y. The process with the wires swapped over, because this is now a distribution on y and x, and sort of the ordering of these matters, because the ordering of these tells us how we can compose it with other things. What is true, though, is that if I have some p, that there will, how do I want to say this? No. That if I have p of x, y, q, yeah. So if I have some p, which is probability distribution on x, y, then there will exist some q, which is a distribution over y and x, such that when I swap the two legs over, I get p. And this is sort of super easy to see diagrammatically. We just define q as p with the legs swapped over. And then we just use the fact that sort of if I swap two things and then I swap them back, that sort of our diagrammatic rules say that only how things are connected up matters. So this is the same as this. So if I swap x and y to y, then that's the same as just. Okay, so I hope that's maybe clarified the situation with these processes a bit.
So another question regarding before we started the stochastic processes. How does it work for parallel processes? So if we come back to the beer and I want to give beer to multiple people, how do I just split the beer wire?
Yeah, so in some process theories, there will be a way to just split an input. It depends a bit on how you're thinking about it. So if you're thinking of, you can think of an input that has sort of beer viewed as a sort of continuous thing, and then I can split it up as I want. But if I imagine sort of I've got a particular quantity of beer, then I can't just sort of freely copy that. I have to say some proportion is going here and some proportion is going here.
Do you start to have weighted wires?
Yeah, for example, you could formulate things like that.
Because I was thinking on something else. You were doing operations. Say to the reader, you're applying the magnetic field. How does it work in the diagrammatic point of view?
There's probably you often have freedom over what you treat as an input and what you treat as you could imagine that the magnetic field is treated as a process that you apply to some particle. And then you might draw it like this. But at other times, you might want to and then you might have something like sort of field particle interaction, and out comes the field and the particle again. And then usually in theories of physics, you would want to have some sort of consistency condition that lets us relate these two lines. Let's call it, I don't know, psi, if it's a quantum field, or to the field afterwards, so we're just going to treat it as discarded. So then we have a way to go from this sort of interaction description to a more sort of process-oriented description.
Let me push just one step further. Now, if the field is changing with time, how does it work?
Again, there's probably lots of different ways to represent this. I could put in some t parameter onto the process. I could put some maybe t parameter onto the state of the field. I could also do something like say, okay, we've got some initial state, psi 0, that then evolves according to some unitary evolution, that then, okay, I've run out of space, but yeah, so again, there's sort of multiple different ways to describe this. But
Like the field is acting as in the way you show it, it seems like it's acting after or before, but I would like to have, like, as I said, two parallel processes.
yeah, so then I think your best way to try and represent that would be sort of putting some time parameter on the interaction, probably, and just describing the sort of holistic evolution of the field and the particle together, and then some time parameter. I should say, though, that usually this formalism is better when you sort of discretize things, and you imagine sort of just, I have the unitary evolution, rather than trying to put in sort of continuous parameters for things. So yeah, this is more suited to like a quantum computation kind of thing, where we have circuits representing the evolution, rather than trying to capture things like the Schrödinger equation. You can do both, but just there becomes a lot of choices over how you're going to do it, and yeah, it's. Yes, you can kind of think of one. Basically, the maximally mixed state often acts as a kind of co-discard, but typically you won't satisfy the time-reversed sort of causality condition. We can talk about that later. I think it's probably a bit too tangential for things here. Okay, so let me move on then. So we were talking about stock, and the basic definition, we have stochastic processes between finite sets, and we've talked about how to compose them and how to see some special cases giving back things that we're familiar with. There's one final structure that it's useful to talk about in stock, which is convexity. So suppose I've got some set of stochastic maps, Si, with input x and output for this variable I, so this is I in big I. Then intuitively, we kind of know we can take convex mixtures of these things, right? So I should be able to define something that is like the sum over I of little pi Si from x to y. And, well, we can define this simply as that this, okay, so this is going to be some f of y given x is just defined to be the sum over I of pi of so we can take these convex combinations of processes, and what's nice in stock is that this diagrammatic representation that I've given here, it has some nice properties. In particular, this convex sum that we've introduced distributes over diagrams. So if I have some, let me just try and give a simple example, sum over I, pi. Then I can, on the one hand, I can take convex combinations, get this new individual SIs with T, and then trying to take the convex combinations of those. So that would be so I've got these two different ways I could try and compute this thing. And what's nice is that actually these two are equal. So I don't need to sort of figure out which bit of the diagram the sum is acting on. I'm sort of free to move these sums around the diagram. So I can sort of get rid of these dashed boxes and just write things like sum over I, pi. And this is an unambiguous equation. So another way to put that is that sort of composition of processes is convex linear, or that the action of T on have another nice way to represent these convex combinations. So we can imagine that we've got some controlled process S from X to Y. Now it's got some extra input, which is the finite set that is this index set that we introduced over here. And it's not too hard to convince yourself that we can get such processes such that if I look at the sort of the delta function distribution, delta on little I, which is going to be illegible to people. So I'm going to just remove this delta and denote the sort of delta function distributions just by the element of the set itself. And I can always find a controlled process S that when I'm fed in a particular value of the control system gives the stochastic map SI on the other pair of systems. Pairing this control system. And so then I can feed in some probability distribution into S. And this is just going to be the sum over I of, so I in I. This will last for about 30 seconds and I'll forget again. Pi Si. So we can always go sort of backwards and forwards between these two different ways of representing convex combinations. I can sort of explicitly write them as convex combinations, or I can sort of dilate my process into over the control variable. And this sort of perspective will become very useful when we go beyond this theory stock and as I think I can now. I think I've said everything about stock that I wanted to. Yeah. Okay, so that was where lecture 1 was supposed to finish. So we've seen now process theories and this sort of concrete example of a process theory called stock that has this nice sort of extra convex structure to it. There's lots of things that sort of process theories are too general for, though, that we can do in stock. So, for example, if we want to talk about cryptography or computation, we can start to sort of express these ideas in stock. But if I give you a process theory for brewing beer, so we're now going to sort of specialize a subset of them that are going to have nice sort of ability to ask information theoretic questions that we care about. And this is going to take us into the world of generalized probabilistic theories. Which are typically called GPTs. There's also another very closely related formalism, which is roughly the same as what I'm going to talk about today, known as operational probabilistic theories, or OPTs. And as far as I'm concerned, the formalism I'm going to present and these two formalisms are all the same as one another. They're sort of different perspectives on the same fundamental mathematical object. So the idea is that we want to describe possible theories of physics that are in some sense compatible with the classical world that we see around us. So the way that we learn about physical theories in practice is that we have sort of experiments, and by using these classical probe systems, we try and learn something about the deeper reality, quantum reality, whatever it is. So we're going to now try and describe a class of process theories that are understood in this sense, via our classical. We're going to formalize this, and then we're going to see that the structure of a generalized probabilistic theory falls out from that perspective. So this is a class of process theories, which is a class of process theories which is compatible with how we actually do physics. So what this means is that okay, we're going to denote some generic GPT by G. And the idea is that this GPT contains stock, all of our stochastic processes. And at this point, I need to start having multiple colors of chalk around to try and keep track of different kinds of systems. So I've been drawing stochastic things which are going to look like this, labeled by some sort of finite set X, which are our classical systems. But we're also going to have other systems, such as this one labeled by A, which are just some other kinds of systems. They might be quantum systems, they might be beyond quantum systems, they might be some system we haven't characterized yet and don't really know what it is. So just other stuff. So we've got these two different kinds of systems in our theory. And for this to be an interesting theory, we're going to have some kind of interactions between these stuff. We don't just want the classical world evolving on its own and the quantum world evolving on its own, because if we had that, then we would never have any hope of learning anything about the the quantum world. So we need some interactions. And there's, diagrammatically, it's simple to sort of start talking about these things. For example, we can imagine that we have some process, let's call it P, which has an input X and an output A. And then the way we can think of this is that this is some sort of controlled state preparation. We can think of this as some sort of lab device that has some control variable, this X, some dial that we can tune. And then we have some other system, A, coming out of it, and this is now going to be in some particular state. And we can talk about measurements. In particular, we can talk about destructive measurements. And destructive measurements in this language are things that have some GPT system A coming into it, and then some classical system Y coming out of it. So this Y then is like the outcome, where the pointer goes to on your measurement device. We could also define sort of non-destructive measurements where A comes out again, or maybe some B comes out again, and a bunch of generalizations, and we'll classical systems and non-classical systems. But this is still a process theory at the end of the day, right? So we can start to compose these things with one another. So in particular, if I have these kinds of interactions, then I can wire them together by the A system. So I have some preparation controlled by the variable X. That prepares the system A in some state. And then I do some measurement to it, which has an outcome, some little y in the set, big Y. And if you do this in the lab, I have some controlled preparation and some controlled measurement. And if I do this a bunch of times, I'm going to get some statistics out of it, or some data that then, in the infinite limit, turns into statistics. So what this means is that this thing should just equal some stochastic map S going from X to Y. So this stochastic map S represents the statistics that you gather when you do this experiment, and see for each different setting of little x, of big X, what outcome.
How do you define classicality or non-classicality in such scenario? Or in this kind of theory?
So I'm just sort of, from the start, just saying there's these two different kinds of systems. There's the classical ones defined by finite sets, and then other systems. Now, these other systems might turn out to be classical systems at the end of the day. Like maybe defining classicality is another big subject, which will be covered a lot in this course, the summer school. But for us, saying that A is some GPT system doesn't forbid it from being classical. It could also be classical. We just don't know at the start. But then these systems X are definitely classical because we've defined them to be classical. They're sort of control variables that we already know how they behave. This is not to say that there's some sort of fundamental notion of a classical system. And actually in my third lecture, I want to talk about how you can see these systems as being sort of emergent from some deeper kind of reality. But for the moment, we're just going to presume that they're sort of fundamentally classical in some sense.
And the convention is if it's X, Y, or Z, it's classical, and if it's A, B, C,
yeah,
could be something else.
And I'm going to hopefully stick to white chalk being classical and green chalk being something else.
Can you use orange or something? We can't really tell the difference from here.
Oh, really? Oh, okay. That is unfortunate. Come back down for me. Is that clever? Excellent. So let's fix that. Okay, and sort of in sort of jargon, what's going on here is we say that stock is a full subcategory or subtheory of the GPT-G, where full just means that whenever I compose a bunch of processes together and I only have classical inputs and outputs left over, then this is going to be some classical stochastic process. Basically, if you try and conceive of getting anything else, then this would be like saying that I'm going to go to the lab and I'm going to try and do this experiment where I vary my classical inputs and get my classical outputs. Then if this doesn't go to a stochastic map, then, well, what does it go to? You would have to, end up seeing negative probabilities or something mad. So this is quite natural to assume that when we compose things together and only get classical inputs and outputs, that this is a classical stochastic map. Okay, but we need to get to a theory that has sort of some nice structure. So we don't want to just sort of imagine that there's a few interactions. We want to sort of say that there's a whole bunch of interactions that we can use, and we're going to now try and formalize this idea. So in particular, we're going to demand that we have all classically controlled processes exist in our GPT-G. So what does this mean? This means that if I have some bunch of processes, let's call them Ti, going from A to B, I in some set I, so for all sets of processes that we have, there exists some transformation T going from A to B with some extra system going in, some classical system I going into it. I do this as red. The color that I draw the boxes isn't really too relevant, so I'll probably not be consistent with that. The important thing is the color of the systems. So yeah, we're going to demand that in our GPT, in our process theory G, that whatever collection of processes that I can come up with, I can always find some classically controlled process where by varying over that classical control degree of freedom, I vary over that set of processes. And this hopefully should look familiar to you because it's exactly what we had over here in stock itself. So stock, then we can see, is a process theory where all classically controlled processes exist. Now we're trying to sort of extend stock by putting it inside this bigger theory, G, but we're trying to lift this property. We're trying to say that even though we don't know exactly how this sort of non-classical stuff behaves, we know that if I can implement a bunch of different transformations, Ti, then I should be able to choose which one to implement using some classical control variable. And we saw over in stock that we had these two different ways to represent convex mixtures. We could just sort of directly take convex mixtures of the processes, or we could use this classical control to define them, to calculate them.
I'm trying to reconcile this statement of them being two quantum. So if we're doing a spin measurement, we will only get plus half or minus half. But so what we are saying is that if at the end of the classical process also the measurement results are discretized, something like that.
So it's not to say that I can sort of come up with, it's not to say that I can replace A in this diagram by some classical system, which is also like a spin system, say. is just to say that the process going from X to Y, if I ignore what's happening in between and just look at the input and outputs, that this looks classical. But it might be using some totally different classical system. It could be just some computer algorithm that randomly generates outputs based on the input. So it's not saying that there's some sort of physical mapping from what's going on the internals of the system A, if A was a spin. It's not saying I can find some classical system to represent A. It's saying that, yeah, the overall sort of input-output functionality, when I ignore what's happening in between and just look at how X transforms into Y, that thing looks classical.
I think maybe the confusion is that you're trying to draw destructive measurements, and he was thinking you meant that Y is the system output, not the classical.
Possibly, yeah. So yeah. At the end of it, if you want to take into account post-measurement states and so on, then we would draw a red system coming out as well, and then this rule doesn't apply, because then we'd have a sort of a non-classical system coming out, so then the whole thing doesn't have to be described classically anymore. It's only if all of the inputs and all of the outputs are classical that we think the thing should be described classically. So in the case of stock, we defined convex combinations of things, and then we showed. Well, it turns out that we can kind of do the same thing here, but in the opposite. And it turns out that we can use this to define convex combinations of processes in our GPT. So we can define sum over I, pi. So we can sort of make this candidate definition of what it means to take a convex combination. And I don't have time to go into this now, but it's either in the lecture notes or will be by the end of the week. You can show that this is a consistent definition and that these sums can sort of float around the diagrams and that everything is convex linear and it all sort of behaves really nicely in the way that you'd expect. But what this allows us to do is it allows us to start moving towards another perspective. And this is how you'll often see GPTs presented, in fact. So we're starting from sort of diagrammatic process theory land, and we're going to work towards convex geometry. In other presentations of GPTs, you'll see the convex geometry as the starting point, and then trying to build up to diagrams and a process theoretic language. So there's sort of two complementary perspectives on things. But we can take convex combinations of processes, so processes all live in convex sets. Okay, so this is our first demand for G. There's one. I'll get there in a minute. Okay. But what we find is that if this is all we demand of our process theory, then there's a lot of superfluous information in the descriptions of the processes. And what sort of the GPT framework tries to do is it tries to strip away all sort of information about processes that is irrelevant to making sort of predictions about the outcomes of experiments. So to try and move in that direction, we want to define what this sort of superfluous information is. So to do that, I'm going to introduce a notion called operational equivalence. And all of this stuff is going to become very relevant again in David's course. So pay attention if you want to understand that as well. Anyway, so we want to define this notion of equivalence, which is I'm messing up my conventions already. T1 from A to B, whoops, is operationally equivalent, which I denote by this little squiggle, to T2, also going from A to B, if and only if all conceivable experiments that I could do on these two processes will not show any differences in the statistics. So what this means, let me define it here, in fact. X, Y, P, M, A, B, C. X, Y, P, M, and C. So this is supposed to represent our sort of generic experiment. We have some preparation controlled by some variable X that prepares the system A and maybe some extra auxiliary system C. And then we apply the transformation to the system A, get some system B coming out of it, and then do some measurements on B and also maybe the extra system coming along and get some outcome Y. So this is it might not be totally obvious. You might think I could draw more complicated experiments than this, but it turns out that whatever more complicated so if you imagined that there was, I know, some third system coming out from P that then goes and is measured by something else with some other outcome, well, then we can always sort of lump things together. We can lump the extra system into C and the two measurements together and so on. So we can always recast things back into this form.
John?
Yeah, so this is all P
theory,
and
or?
M in G.
Okay.
So we have G, which is our process theory, which defines our sort of the world that we're living in and the scope of possibilities. And within this, so these quantifications live inside the process theory.
And does this include using T1 multiple times? Or do I think about it as...
No, this is like a one-shot sort of thing. Yeah. So this is our notion of operational equivalence. And so it's not difficult to see that this defines itself. If T1 is equivalent to T2 and T2 is equivalent to T3, then T1 is equivalent to T3, and so on. So this allows us to define equivalence classes of processes. And we're going to denote the equivalence classes, the operational equivalence classes. We'll denote by T tilde. So this is defined as the set of T primes such that T prime is equivalent to T. So this is just set, and that's our equivalence class. So now, given any process at all, so given some process T, we can always compute its equivalence class T tilde, or we can define its equivalence class T. So given some T, we can always say that this is equal to sort of its, or defined by its equivalence class, and then some extra information. And we're going to call this extra information C sub t. And I won't go into details about what this tells me which element of this class I am. And this is known as the context for the process T. So every process T can be defined by its operational equivalence class and its context. So you can see this is the same context that will appear in the context of contextuality later on in the week. But these contexts, they have absolutely no bearing on any experimental outcome, right? It's by definition the we really want to get rid of this extra information. Okay, so how to put this? There we go. Let me just check I'm not missing anything important. Yeah. So So this is sort of the key next step that we're going to take to getting towards generalized probabilistic theories, is that we want to remove all of these irrelevant contexts, and instead just work with these equivalence classes. So what this means is that we want, sort of formally, this is we quotient this process theory G by this equivalence relation squiggle to get new theory, and we denote that as G quotiented by this equivalence. This means. So let's define this quotiented theory. So processes, well, actually, let's start with systems because they're easy. G are still the same systems that we had before, so nothing changes there. Processes in the quotiented theory are simply the equivalence classes in G. So they're denoted by, whoops, wrong color, by things like this. So this is the equivalence class of processes, is now itself a process. But I need to define things like how these compose with one another. So let's try and draw something generic looking. So suppose we have some T, and so T tilde and some T prime. Then the way that we define this is we pick some representative element for this class and some representative element for this class, and we compose those together, and then we quotient that. Actually, this example is kind of awkward to notate, so let me get rid of that one. It's useful to talk about sequential and parallel composition. So suppose we have T tilde composed in sequence with T prime tilde, then this is defined as T prime composed with T quotiented. Now, a priori, this is not necessarily a good definition, because I said that this T prime could be an arbitrary choice of representatives from this class. And this T could be some arbitrary choice of representative from this class. And so for this to be a well-defined sort of operation, it's got to be the case that this is independent of which choice I make. And in the lecture notes, this will be spelled out in detail. But choosing different equivalence classes would lead to different equivalence classes is when we compose those together. Well, that's basically just describing some experiment, right? Okay, it's an experiment where now M, this choice of representative for T prime, and then do some measurements. So essentially, if this wasn't independent of the choice, then you'd be able to cook up some experiments that then saw a difference between the elements in that class, and so we would have sort of inconsistency. So this notion of composition, you can persuade yourself, is well defined. And okay, similarly, for parallel composition, we can define D tilde prime. I should have made all of these red systems, sorry. Whoops. Okay, so the same definition holds for parallel composition as well. We pick representative elements of the equivalence classes, compose those in the original theory, and then construct the equivalence class of the composite process. And again, you can show that this is all consistent. Yeah.
When you mention T as tilde, it's defined as T tilde and then CT.
Yeah.
So T tilde prime will have a different context, right?
Yeah. It's just part of the that a process theory, we haven't said there aren't contexts, so that there may be contexts. In terms of physically what a context is, if we want to talk about contextuality, I'll probably just point you to David for that one. But it's just sort of, to give one example, in quantum theory, it might be different convex decompositions of a density matrix are all going to lead to the same operational predictions when you do measurements on the quantum system. So then the difference between different convex decompositions of a density matrix would count as the context for that density matrix. So like the density matrix is the equivalence class, the description of the convex decomposition is the context. But yeah, I'll deflect details on this kind of stuff towards David's lectures. Okay, and then we talked about how we had these nice classically controlled processes in G. 5 minutes left? Okay. So we had these nice classically controlled processes in G, and we could use those to define convex combinations. Well, conveniently, that wasn't in vain, because all of that also follows through to this quotiented theory as well. So in particular, if we want to define some convex combination of our equivalence classes now, then we can define this as, well, the notation is so the basic idea is that, again, we pick our choices of representatives, some ti for each of the ti tildes. We pick our representatives. We use the tools we talked about over there to take a convex combination within the process theory G. And then this defines our convex combination in the quotiented theory. Again, to make sure this is consistent, you've got to make sure that all of this is actually independent of the choice of the representatives that you make. But the idea behind the proof of that is the same again, is that if you could find some sort of contradiction with this, where it depended on the choice of representative, then you'd be able to cook up some experiments that could be used to distinguish these things. So we get that G tilde, G sort of quotiented, in controlled processes, we've got convex combinations. It is a process theory. Theory of equivalence classes is very nicely behaved. I'm running out of both time and space on the board, conveniently, roughly at the same time. So the final thing I want to mention is causality. And typically, when you're working with back to our theory G, we assume that all effects are operationally equivalent. So all ways of throwing away a system will lead to the same probabilities at the end of the day. It'd be kind of weird if it didn't. If it sort of mattered how I discarded a system, I could somehow create an experiment to witness that. It would be odd. So it's natural to make the assumption that all effects in G are equivalent to one another. I suspect this is going to cause confusion later on, but take this for granted for the moment. Hopefully things will be clarified tomorrow. And then what this means is that when we go to the quotiented theory, then we only have a single equivalence class of effects, and so we end up just with a single effect. So all effects are operationally equivalent in G, means that we have a single effect in G quotiented, which will denote, should be a red one really. So every system in the GPT has a unique way to discard it. Okay, so at this point, this is really the sort of process theory view on what a GPT or an OPT is. We start with a theory that's got classical stuff and non-classical stuff, and they are demanded to interact such that you have all of these classically controlled processes available, giving you the convex structure. And then we try and remove the sort of operationally irrelevant context information by this sort of quotienting procedure, and we get this theory G quotiented out at the end of the day, and that is the GPT or the OPT. There's a lot of sort of convex geometry that you can then study once you have these definitions in place. So I think I'll start to talk about that side of things tomorrow. For now, though, are there any questions?
Non-associative process theories to a more general thing.
So no, basically. It depends exactly what you mean. But sort of parallel composition of processes is always associative. Sequential composition of processes is always associative. You can sort of lift things to a higher level and then have processes that themselves are sort of the composition of things. So I could draw let me squeeze in something here. So I could draw something like some process which is taking the tensor product of two things, whatever these things are. And then you can express a sort of an associativity condition for this kind of object, which basically says that this equals this. It's like if I lump these two things together first, and then this one is the same as lumping these two things together first, and then this one. And so sort of while composition, like parallel and sequential composition, have to be associative in a process theory, we can define processes within a process theory which capture sort of non-associative binary operations. So if it was non-associative, obviously that would just become a not equals rather than equals.
Okay, if there's
More
no
questions?
more questions for now. Yep.
Mm-hmm.
Of T1 doesn't necessarily have to be operation equivalent to two uses of T2, but isn't in some sense that the content of this composition rule, or I think I'm missing something basically.
Yeah, it might follow.
Okay. So it is in there that maybe it is even a multi-copy equivalent is somehow hiding in these definitions.
Yeah.
Thank you.
Yeah, it's just not part of the sort of fundamental definition, but it seems to follow from the definitions. Yeah. Mm-hmm.
The whole effect of operational equivalence in GPT, how's this equivalent to causality, the assumption of causality?
Yeah, so this is something that I skipped over a bit. I wanted to talk about it a bit more in the first lecture. But the basic idea is that if you have a theory with a single effect, then this means that all processes have to be discard preserving, because otherwise this would give you a way to define more effects.
You mean the single effect that there's only one effect defined in the theory? Okay.
Yeah.
Like the discarding effect.
Yeah.
It has to include the discarding.
Yeah, so it has to have the discarding effect, and then there's no others on top of that. And then once you have this rule, then you can prove of systems. And if you imagine that the systems now propagate along sort of light cones, then this means that your process theory is, in that sense, sort of compatible with relativistic causal structure.
Because it has discarding or preserves discarding.
Yeah. Yeah. Basically, if you had lots of different ways of discarding a system, then that would end up allowing you to sort of propagate signals without needing to transmit a system. Like Alice could signal to Bob without needing to send a signal to Bob. And then this would be sort of in contradiction with sort of special relativity, hence this sort of term causality.